Hello everyone, welcome to this material characters course organized by NPTEL. And in the last two tutorials we have been looking at the solving the electron diffraction pattern, and we have just looked at solving single crystal electron diffraction pattern by choosing two methods, one by selecting the diffraction pattern directly and then find out the zone axis, or you can always start with the zone axis by guessing and then arrive at the particular zone axis with specific indices. And then the last one which is left over in this tutorial problem is looking at the ring pattern or polycrystalline electron diffraction pattern. We will just look at the general procedures, how to deal with indexing this polycrystalline electron diffraction pattern. So, I will just lay out some of the general procedures what is being followed, and then I will also take up some specific cases, a simple system like a cubic system, and then we can adopt this general procedure to any crystallographic system. So, let us just start with the procedures for solving the electron diffraction pattern in the case of polycrystalline material. So, we know that this is the relation which we have in the from the geometry of the transmitted and the diffraction system in the electron microscope. R d is equal to lambda L, and d is the interplanar spacing, r is the distance from the center spot or a transmitted spot to any of the diffracted spot in the case of a single crystal pattern, or it is just the the measure of radius of the ring in a polycrystalline diffraction pattern. Lambda is a wavelength and L is the distance between the sample and the final screen where it appears. So, the product of the lambda and L is considered as a camera constant, which we have already seen, and we can calibrate this, that I will talk about little later. So, this is the basic idea with which we are going to work out. So, let us take the ring pattern. So, what we do, suppose if you have the ring pattern of this kind, let us talk about a general procedure. Suppose if you have the ring pattern like this, then we can now consider a simple system, probably a cubical system. So, in case you can write, let us take one cubic system for example, because which is very a well known system. So, let us take that. So, we can write for that, you know that in a cubic system d is equal to lambda L, and this you can write as equation 1, and we can rewrite this equation R is equal to So, what we have done here is for the cubic system, we know that d is related to this with the a, the lattice constant, and then from that we can rearrange this into r square value. So, what we have written here is all r square values are proportional to some number or ratios of some number. So, when we take this h square, l square, k square as a n, that is as the sum of all the integer, it will not have any value of n with it, such as for example, it will not have 8 n prime minus 1 values where n is an integer. So, for example, if you substitute this, n can have only values like you can just put it like this 1, 2, 3, 4, 5, 6 and then 7 will be missing, because if you put n is equal to n prime is equal to 1. So, 8 minus 1 7 will be missing. So, then it is 8, 9, 10, 11, then the next number will be missing, something like that. Suppose if you put 2, then it is 16 minus 1, 15 will not be there here in this series. So, this is one way of putting this, and then we can create a table for all these different n values. And what we are now trying to do is, we are trying to take a general procedure, then we will compare this capital N according to the specific crystal system, because we will be able to look at the allowed reflections and then try to match with any one of this the sum of the integer values, and then try to arrive at a possible solution. So, we will take up some general idea. For example, in the case of simple cubic, all values will be applicable. All the values will be applicable. But if you go to BCC, that is body centered cubic lattice, you will have 2, 4, 6, 8, 10, 12, etc. So, like that the allowed reflections. Similarly, we can write for FCC, you have 3, 4, 8, 11, 12, etc. So, it will go like this, and we can write for looking at the ring pattern some general remarks. If large number of rings are seen, then this is probably a simple cubic. It is only a guess. This is BCC. With r squared changing in certain fashion. If two lines very close and the third line at a distance, and so on. So, when you look at the polycrystalline pattern, these are some of the general remarks you can look for. If the large number of rings are seen in your diffraction plane, and it could be a simple cubic, just give you a first idea, first impression. And if the lines are equally spaced with the r squared changing in certain fashion, we will see, I will make a table and then tell you what does this meaning. When r squared values, what you have shown here, when it changes in a particular fashion, then we can guess this could be a body centered cubic crystal system. And if the two lines are very close in a, because all the polycrystalline ring pattern will appear like a concentric rings, in those pattern, if two lines are very close and the third line is at a distance and this pattern repeats, then it could be a face centered cubic lattice. So, that is the first impression you can get. These are all some of the observations you can keep in mind, so that you can quickly come to a conclusion, and then later you can confirm that with a proper analysis. So, that is what we are going to do now. So, for example, you can do start measuring R number R by R1. So, the another general observation is, suppose if you measure the rings, different rings in a polycrystalline pattern like this, and then take the ratios with the smallest radius and then tabulate it like this. So, The measurement is to be very, very careful whether it is a single crystal pattern or a polycrystalline pattern, because each person will have its own human error in measuring that. So, when you in a general case like this, so the initial values, the error will be large at the beginning, then as you go down the error is small. So, it is always to try to take different rings and then take an average for a to minimize this error. So, that is one general remarks one should have. For example, we can now try to tabulate this in a general form. You see, what we have now done is just whatever I have we have written there in the previous section, we have just start comparing with the simple cubic systems. One is simple cubic, this is body centered cubic, this is a face centered cubic. You can see that your simple cubic varies with this R by R ratio, and then what I mentioned is your the other ratio goes in this fashion. Suppose if you do this kind of tabulation, and then for an FCC it goes like this. So, you know that again you can do this lambda L, you know that R is equal to lambda L by A, and R1 is equal to lambda L by A, and then R1 by square root 2 is equal to lambda L by A approximate. So, that is how you calculate for this particular system. So, this will be an approximate number, but then it will follow this trend for the in the case of FCC. Now, based on this, I will just follow we can also make table with simple you can also make table like this. This is from the book K.W. Andrews et al. It's a book. Interpretation of electron diffraction patterns. So, this example which I am going to give, table going to give from this book, K.W. Andrews et al., Interpretation of Electron Diffraction Pattern, published by Springer Science in 1967, and very useful table which I am going to show. This is line number. You can put n is equal to h square plus k square and HKL indices. Root n is equal to root of h square plus l square plus k square. It should be PCC, FCC. So, take this 1, so you have 1 0 0, this is 1 2 1 1 0 1.414, this is 3 111 1.732, it will be 4 2 0 0 2.000, it will be x x 5 0 2.236 . So, what I have drawn in a table is general indices, and this is your n value, and this is square root of n, and which is corresponding to your allowed reflections in the both the systems. So, you can see that as I mentioned in the beginning, you see that 8 n prime minus 1 n will be absent. So, 7 is absent here, and you can see that in BCC reflections are tabulated here, and similarly FCC reflections are tabulated here, and that is how you can compare these are standard tables which will be available. So, whatever the table you generate from this r values or r squared values, you can relate that with the n by putting these tables. Of course, you have to remember that this is a simple cubic system. For other crystal systems, you will have a particular d spacing relations. So, you have to accordingly make a table and then compare this ring pattern. So, that is the one important aspect of analyzing this. We can now write general rules this is again from the So, what I have written here as a simple procedure for indexing ring pattern, there are two cases you have to remember. One is when the identity of the substance is known, then you just follow this procedure. First you measure the diameters of the ring d and convert these distances into interplanar spacing values, that is d value small d via camera constants. That is what we have done here in this table, that is what we have done, and compare the measured d values with the standard ones for the particular substance, and then each ring can be indexed like this. You have to just measure the distance and compare the d values, and confirmation can be done even with an X-ray work if possible, or if it is necessary. And if it is an unknown substance, then follow these procedures. So, similarly measure the diameters first, then convert them into diameters through camera constant, and then look at this some of the general remarks what we have stated already. The arrangement of rings may give some clue, that means whether they are a large number of rings or do they have some do they fall some particular symmetric fashion. Something like your FCC, you have a two closely spaced lines will be there, and then third line will be with some distance and so on. So, you look for some clue from the arrangements of the ring, and then use the index where you have the camera constant d value with the standard crystallographic data or the d spacings index. You can look at them, and then also finally you can do X-ray diffraction to confirm that whatever we are analyzing from this. So, these are some of the standard procedures for analyzing the ring pattern. Now, we are talking about camera constant. So, I will now just briefly tell how to do the calibration for the camera constant in the case of analyzing this polycrystalline material. So, same procedure, camera constant is lambda L, can be written as R G H K L is equal to R T H K L. This particular method is from reference electron optical application in material science by L.V. Moore. So, here again what we have trying to do is, this is from the reference electron optical application in material science by L. E. Moore, and what we are going to do is from this relation how to do the calibration of the camera constant. So, so R, this is G HKL is a diffraction vector which is related to R D HKL, and D HKL is the interplanar spacing for a particular system, for a particular plane HKL, and R is the particular diffraction ring radius. And if you take a cubic system, then we will write HKL then we can rewrite this into so this form of the equation appears like a straight line equation. So, we can say that suppose if you put this into y is equal to mx type, then we can write y is equal to h square plus l square plus k square, m is equal to a by lambda l, and r is equal to x. R, I would say x equal to r. Let us be uniform here. So, we can put it like this, and we can now draw one schematic to show this. Suppose if I have the diffraction pattern like this, So, what we have done here is, so we have taken some cubic system equation, and then we see that if you write this equation in this form, it is a straight line equation. So, we have taken one polycrystalline pattern which actually appears like this. In the case, this is the particular case of nickel, but then the message what you are trying to get from this is, if you plot this h square plus L square plus k square square root versus r, the intersection. So, the intersection of the corresponding values of this square root and the ring radius for the allowed HKLU values depends upon the particular cubic system, but in this system it is nickel. So, like that if you plot, then you will, the slope is nothing but your camera constant. If it is done for a known system, then you have the value of camera constant, and if you can use this camera constant for a given acceleration voltage, and you can use that camera constant for analyzing the unknown pattern. If you operate the microscope in the same condition, then that is valid, and this is another way of calibrating the camera constant. So, that you will have that value, you can just simply plug in and then find out the d spacing for the unknown material. So, this is another way of looking at the same procedure, but then it gives you a kind of a simple procedure to plug in this d values and find out the camera constants. Thank you.